right. Thanks. So hi, I'm Gordon. I work at a company called Ada. Our facilitators tonight are Xiyang and Alok, right here. And so we're going to be talking about DeepMind's paper on Grandmaster level in StarCraft II using multi-agent reinforcement learning. So I'm curious, who here is here for the reinforcement learning? Okay. And who's here for the StarCraft? Okay, bit of a split. So it's quite a large paper they publish in Nature, and there's a lot of supplementary details. So did our best to condense the paper into presentation. There definitely will be things that we're skipping over. So if there's something you want to know more about, just raise your hand and ask, and we'll do our best to cover all that. And yeah, I guess I'll get into it. The outline will be, so talking about StarCraft first, what is it? Why did they choose it for this paper? And then getting into AlphaStar, which is the agent that they created to play StarCraft. And we'll break that down into talking about how they use supervised learning or imitation learning, reinforcement learning, and self-play, and then this concept they call the league that they introduced. And then we'll get into the results and analysis after the break and have some discussion. So yeah, let's get into it. So DeepMind's mission, as their founders and website stated, is to solve intelligence and to use it to make the world a better place. And so this work is largely focusing on the first part of that, solving intelligence. And so yeah, StarCraft II is a video game, for those of you who don't know. And so they're hoping that some of the work that they did here can transfer to other areas to make the world a better place. But the actual focus on StarCraft is just on intelligence. And so this is following in a pretty strong tradition of applying machine learning to different video games for quite a while. These are just some examples. Several of these, I think the first three were from DeepMind themselves. So Atari video games, Super Mario Bros. And Quake 3. And then this year there was a very big publication coming from OpenAI. They called it OpenAI 5, where they trained an agents to play the game of Dota, which is similar to StarCraft. It's also a real-time strategy game. So if you haven't taken a look at that one, I also encourage you to take a look. So why StarCraft in particular? Why did they choose this game? And I think one way to put it is that because it's really hard. It's a very complex game. These are some quotes I found online. The first one is actually from someone who commentates StarCraft videos. So it's kind of like chess on steroids. It's like chess in the sense that it is a strategy game, but it's a real-time strategy game. So whereas with chess, you're making one action over generally a longer period of time, in StarCraft, you're making many actions per second, multiple per second. And there are also mechanical limits, which you'll see in a moment. And yeah, it's generally very hard to play StarCraft perfectly. So it's a very complex game. And when you compare it to a game like Go, which is a board game that's been around for 2,000 years, that I believe last year DeepMind trained in agents to play the game of Go strictly through self-play. And so comparing the two, again, they're both strategy games, but in Go, like with chess, you have perfect information at every time step. So you know exactly where all the pieces are, and same as your opponent. With StarCraft, you have imperfect information. So there are certain parts of the environment or the map that you can't see at any given time. And those could be areas where your opponent could be taking some action or doing something, but you just won't have knowledge of it. So that's one significant point. With Go, there are 371 tiles on the board where you can place, or points where you can place a tile. And so the action space, although the number of possible games is really large, the number of possible actions per turn is quite low compared to StarCraft, which is reported around 10 to the 26. So in each moment, you have that many options for what action to perform. And obviously, the number of logical actions that you would perform is much lower than that, but still, it's a really big action space, and that's another big challenge for a reinforcement learning agent. Also, in Go, there's only one player combination, white versus black. In StarCraft, you have 3 different races, and so in each game, you can have any combination of those races. So there's 6 total player combinations. And Go is a fairly simple environment in the sense that it's a board, a 2D board with a grid structure, whereas in StarCraft you have a very complex environment. A lot of information is available at any given time, and it's changing quite rapidly. So I mentioned the 3 races. These are, oh, question.
Is it 361 for Go?
361
points?
I checked in a few places and it seemed to say 371, but there are different boards that you can play in Go. So this is the 19 by 19. Someone wants to run that calculation, but anyway, I don't think it matters too much right now, but we can follow up after. So yeah, you can either play, the first race is called Terran. They're sort of the human-like units. The second one is Protoss. They're the telepathic, sentient alien race. And Zerg is the sort of insect-like alien race. And so StarCraft, the original one, has been around since 1998, and really a key point of why it's been considered such an interesting and challenging game for so long is that each of these races has distinctly different units and characteristics, but none of them is inherently better than any one of the others. It's very well balanced, and that's integral to the game. So this is an image of what very simple gameplay looks like. So just to get you a bit familiar with the environment. So this is the Protoss race, and you see that big structure is what's called a building. That's where you can produce units from. And the small little units are called workers, and use those to build buildings and to extract minerals. So right now they're extracting minerals and bringing them back to the base. So the general idea is you mine resources and use the resources to build buildings and units. The goal of the game is to destroy your opponent's base, all of their buildings. And so generally you'll need to train army units in order to do that. And usually what will happen will be you'll have 2 players having their armies fight, and when one army is defeated, then that player will usually surrender. This is what a battle sequence might look like. You see the units in blue. This is actually AlphaStar from a year ago when they first did their first demo, and the human players in red. And so you can see if you look at the human units, the red units, each time you see them sort of moving back and forth and shooting and building something in the top there. Those are all actions made by the human. So you can get a sense of how quickly they're taking action. Any questions about the game so far? And you can actually see how many actions they're making. This is a professional player, I believe. And if you just look at his left hand, you can see how many clicks he's making per second. Average professional StarCraft actions per minute in a game is usually around 200 to 400, which means you're taking over 3 actions per second. So it's very quick. And then that can spike to even higher levels at certain points. So DeepMind worked with Blizzard, which is the company that created StarCraft, to create Pi-SC2, I think about 2 years ago. And this is the Python tool to basically enable people to train agents to play StarCraft II. And so it's open source, anyone can use it, but it seems like it's mostly been DeepMind that's been creating really successful agents from the environment. I think their initial goal was to train agents using purely visual features. So just based on what the camera would see here to play the game. And where they ended up is, I could be wrong about that, but I'm pretty sure. And so you'll see that where they end up is slightly different than that. And the first version that you saw a brief GIF of, AlphaStar v1, I guess, was demoed late last year, and has some very key differences from the one that they published in this paper. So that agent had complete view of the entire map, so that imperfect information that I mentioned earlier was not a factor. They were able to see everything. And they did put some restraints on how many actions it could take over a given time span, but it wasn't enough to prevent it from taking superhuman spikes in action rate in certain situations. And as well, it was limited to just playing with and against the one race, that Protoss race. Actually, I don't know if I pointed this out. So see in the corners here how it's sort of blacked out? That would be an example of an area where you can't see what's going on. And so there could be an enemy unit right there, and you would just have no idea. The bottom left shows the mini-map, which is basically just a high-level view of the overall map. Okay, so for the current version of AlphaStar, these are all of the input features that go into the huge network that they trained to play the game. So you don't necessarily need to read everything here. The key takeaway is it's mostly broken down into entities, which represent the units and the buildings and those minerals that you saw. So those would be characterized by one-hot encoded vectors like unit type. And then you have status, which might tell you how much health. Am I still on the Wi-Fi? Pardon me?
Can you reshare this?
Reshare? Sure.
Probably lost his Wi-Fi.
Okay, I need the voucher. Or I can just hotspot.
Do you have one?
Yeah. Good?
Yep.
Okay, sorry about that. Okay, so yeah, as I was saying, unit type would be one characteristic of entity. Status, how much health does it have? Any other characteristics of the unit or building? The map information, so this is more the visual positional information. And so yeah, you have several different characteristics here. The height, the sort of the terrain, entity owners, so who owns which entity that are in the map. And as well, you have some sort of, so they say player data, so which race are the two players playing, what upgrades to the units have been purchased, and as well sort of the current camera position. So you can scan your camera across the minimap. That's one feature, and how much time has elapsed in the game. So those are all the inputs to the network, and then the outputs are actions. And actions are characterized by these fields, or these characteristics. So the main one is action type. So do you want to tell a unit to move somewhere, or to attack something, or build something? This is the action type. The selected units are the entities that will perform that action. The target is where they'll perform it, so where to move to, what unit to attack. And then they have queuing, so whether to do this repeatedly or not, or sorry, immediately or later, repeat. And then delay, each time the network outputs an action, it'll also output how long it should wait before it takes the next observation in from the environment. And I'm actually not sure why that was necessary. So the whole network, which we'll show the diagram of later, boils down to this policy network that is conditioned on a state at a given time step, which is characterized by all previous observations of the environment and all previous actions. And as well, this statistic Z, which is corresponding to human data. So there is some level of supervision that we'll talk about, and that's represented by Z. And so at any given time step, based on Z and the state, the policy will choose an action. Question?
My paper didn't through all the pages. I ran out of paper. So there was just one detail I missed, which was, is there a sampling rate, or how do they determine the samples that constitute T for states?
The sampling rate for the
Like,
human data, or
for example, this policy, or for a lot of these inputs, what is T? Is this like,
what is T?
is this like they're sampling from the visual field at a specific sampling rate, or is it some
Right.
transition between?
Yeah, so the rate at which they make actions or receive observations, it's dependent on a few things. So one is this delay. So again, each time the network chooses an action, it will also choose how long to wait until the next observation is made. So in a sense, the network itself determines how long until it should take in its next observation and make its next action. I think there is some default for that, but it's also, they also have some constraints on how many like the overall action rate of the network. And so that is also factored in to the frequency of which it makes actions. So what they tried to do in order to make it a fair test, ultimately they wanted to play against humans, was to basically cap the number of actions, the action rate of the agents, to be in line with what humans are capable of. So does that answer your question?
Give more information. I'm
Okay.
just a little confused as to, it just specifically in the description of the policy, how T would be decided. But I'm sure maybe it'll become more clear as to.
Okay, yeah, maybe we can continue, and then, but please, if it's not clear, let us know. Okay, so this is a quote from DeepMind's blog on AlphaStar. Even with a strong self-play system, there would be almost no chance of a system developing successful strategies in such a complex environment without some prior knowledge. And so this is, I found this quite interesting and something I'd like to return to at the very end in the discussion. But again, talking about how complex this game is, ultimately DeepMind, I think their initial goal was probably to do a pure reinforcement learning approach, but they came to the conclusion that that just was not feasible based on the complexity of the game. And so they came up with a method for doing some sort of supervised learning or imitation learning, I think is maybe more appropriate. So what they did is they extracted or downloaded close to 1 million human replays from the top 22 percentile of human players. And for each player, they extract this statistic Z, which characterizes the actions that the player took in that game. So I'll talk about that right now. And so Z is representing a player's build order and cumulative statistics. So in StarCraft, build order simply means the first 20 units and buildings that you create in a game. And so usually long-term strategy is very tied to the decisions you make at the early stage of the game, and therefore the first 20 buildings and units is very valuable information to transmit from human to agent. And then the cumulative statistics are units, buildings, effects, upgrades that were present over the course of a game. And so 10% of the time they set this to 0 and allow the agent to learn on its own. And so during the supervised training, what they do is at each time step, they input the current observations from the game, from the environment, and they output, the policy network outputs a probability distribution over each action. And so they take that distribution and compute the KL divergence loss between the distribution and the statistic Z. And so that's the main part of their loss function for the imitation learning phase. They also compute the L2 loss of the policy network and then apply updates using Atom Optimizer. So basically, it's imitation learning in the sense that there's no, I guess there's no true label, but they're taking a distribution and trying to bring the agent's output distribution in line with the human distribution. Any questions so far?
Each step and comparing with humans is like the same state or similar. How do they get that similar state?
How do you get the
similar state between human and because it's dynamic, so how do you know that you are the same, like similar state of the image?
Right. That's a good point. I mean, you do have access to the full replay, so you can take it at each moment. I'm not sure about this, but I think the Z statistic might be computed just once for the entire replay. So yeah, I'm not sure exactly what the implications are if you're early on in a game. You might not have even created 20 units, how that would affect the loss there. But that was my understanding, is that it's just one statistic for each game. And that's randomly sampled. So they'll just randomly sample a human replay and compare that, use that as the supervised signal for the agent. And then resample. And then once they've done that, they further fine-tune by taking 16,000 games from the very top players and training on that. And what they find ultimately is that these supervised agents, the agents that are just trained on supervised learning, are actually capable of building all the units in the game. And they are qualitatively diverse from game to game. So this was the starting point, but not the end point. And ultimately, all the other agents that you'll see in the rest of this section, they're all initialized from the output of this stage. So the supervised learning agent, supervised agent, is the starting point for all of the reinforcement learning-based agents. So the weights of the policy here are where they initialize the weights of the policy for the other agents. And so that takes us to the reinforcement learning. Here in this game, in this environment, they define the reward as the match outcome, and they don't discount that. So you only have one reward given at the end of the game, 1, 0, -1 for win, tie, loss. And they use the actor-critic paradigm for predicting the expected reward at time t with the value function, and using that to update the policy. And then as well, even at this stage, they still use the Z statistic, so there still is an injection of supervised signal during the reinforcement learning phase. So they define these as pseudo rewards coming from the Z statistic. But pretty much all the way through, they continue to send those signals through. And so the idea is that actors generate state action trajectories, so sequences of a given state and then a corresponding action. And asynchronously, you have learners who update model parameters. And then, first of all, they store replays in a buffer. They use a replay buffer to store trajectories. And then the learners update the model parameters, which update the policy that the actors are using. policy is updated using vtrace and upgo. So these are pretty modern, very recent reinforcement learning algorithms. Upgo was in fact introduced in this paper. TD lambda is what's used to update the value estimates. This is pretty high level, so if we'll skim through it now, but we do have some slides in the appendix to go a bit more in detail if anyone's interested. But yeah, again, there's a lot of material. And any questions at this moment? Okay, so I think I might have mentioned the concept of self-play earlier. This is really common in agents that are playing games. So certainly for the Go agent, it was trained by playing itself a lot. And again, these images are from the DeepMind blog. A common pitfall in self-play is you can create agents that sort of enter cycles. And the game of rock, paper, scissors is a good sort of visualization of this, although this is a very different game, obviously. So you might create an agent that learns that playing rock is really successful against playing scissors, and scissors beats paper. So it might sort of build up a policy of always playing rock, and then all of a sudden find out that paper defeats rock. And so then it might start playing paper a lot, and then find out that scissors beats paper, and then start playing rock, and basically create this loop. And then that's caused because it's not able to retain previous information that would have told it that paper defeats rock. It's not a good example because for any statistical agent playing this game, there's no strategy. But with StarCraft, there certainly is. And so here's an example in StarCraft. Here, V, I, and S are three different units in StarCraft. And each one of them is strong against one of the others and weak against the other one, which is what the arrows represent. And so what can happen if you just do naive self-play with StarCraft, you can have agents that start specializing. So let's say they start building one particular type of unit, in this case V. And so that means they'll become really good at beating armies that are composed of unit I, which is what the purple line is kind of representing. But they've really overfit and over-optimized to that particular unit, and which means they're very susceptible to unit compositions of unit S. And so this is another thing that DeepMind introduced in this paper, is this idea of exploiter agents or exploitation agents. So the idea is the main agent starts playing with a certain mixture. It starts maybe specializing to one particular unit. And then you have an exploiter agent that identifies the weaknesses of the main agent. And the main agent is allowed to learn from that information. So in the end, the green dots pursue a more sort of robust, diversified strategy.
I think read my step for that.
It's void ray.
Oh, really?
Yeah.
Oh, okay. Never mind. Let me check.
Okay, so that leads us to this idea, another idea that they introduced called the League, which is pretty interesting. So the League is a multi-agent reinforcement learning algorithm or framework. And the whole idea is you have agents that learn for a period of time and then are frozen. And by frozen, I mean their policy networks are no longer updated and their weights are just become static in time, but they remain as valid players in this league. And then the new agents that are spawned play against the other current agents, the other new agents, as well as the past agents, past players. And so this does a couple of things. This addresses the issues with cycles and forgetting, because all of those historical players remain as valid, historical agents remain as valid agents, or sorry, players in the league. So the new agents are always having to make sure that as they develop new and better strategies, that they're still able to beat those old agents that were produced a long time ago. And it also leads to diversifying the strategies of the agents. So one way in which they do this was not an idea they introduced. So fictitious self-play is where you have agents play against all previous players in the league. And they basically just do uniform sampling. So you just randomly take any player from the league and play a game, and then take another player, randomly play them, and learn from all of that. And so on the positive, this addresses the issues with cycles and forgetting, because you're always playing historic agents. On the downside, though, you end up having a lot of unnecessary games played, where you have opponents that are very easily defeated, and you're not really getting much signal or learning much from the interaction. So to address that, they introduced an idea called prioritized fictitious self-play. And so instead of uniformly sampling from opponents, you sample strategically. So if you have agent A, for which you're trying to find an opponent, you would sample opponent B from a candidate set C with this probability. So this is the equation for prioritized fictitious self-play. And so you can see that there's a weighting that on the probability of A beating B. So the general idea is you want to choose opponents for whom you think you will not perform as well against. So you want to bias yourself towards challenging opponents in order to get a stronger signal and learn faster. Any questions so far? Okay, so there are 3 types of agents in the league, and the first is the main agents. So I've characterized them as the champion. These are the agents that you want to train to be the best StarCraft II agents in the league, and ultimately the best agents that will play humans. So these agents, 35% of the time, will play against copies of themselves, so just self-play. And 65% of the time, they'll do prioritized fictitious self-play against all past players. And then after every 2 times 10 to the 9 steps, so actions, they are, again, frozen and added to the league. And then a new main agent would be spawned. And they're never reset. So they're initialized to the supervised agent at the very beginning, but each time a new agent is spawned, it's spawned from the most recent main agent. So they're never reset all the way back, their parameters. Unlike the main exploiters, who I've characterized as the sparring partner, and so their goal is to highlight weaknesses specifically in the main agent strategies. So if you think of the main agent as the champion that everyone's trying to train up for the tournament, the exploiter is the sparring partner that's helping them get better faster by identifying weaknesses. So they play 100% of the time against main agents, and they're added to the league. They're frozen and added to the league after a certain amount of success or a timeout. And they are always reset to the supervised parameters. So every time a new main exploiter is created, it's starting with the network of the supervised agent. And that's the idea there, is so that you can encourage diverse exploration of policies. And then the last one is what's called the league exploiters. And so this is kind of like a coach. The goal here is to highlight weaknesses in the overall league strategies. So they're playing against all past players in the league, and their goal is to identify overall weaknesses or areas that the whole league has not considered. And so you might have a case where not just one agent sort of overfits to a particular strategy, but you have a whole group of agents kind of moving in one direction. And so the league exploiters are meant to identify those. And then they're either reset to the supervised parameters with 25% probability or continued off from where they left. Okay, and then this is the mega architecture diagram that they included with a TXT file to explain it. And so at the bottom, you can see the input features. There's a variety of scalar features that we talked about earlier. Entities, these are the units and the buildings, and as well the mini-map, the visual features. So they actually use transformer networks that are common in natural language processing these days to embed entities. Not exactly sure why they chose that structure, but basically they take all entities, all units and buildings, and I think they have, double-headed transformer network that embeds those and then feeds that into a deep LSTM and as well into the ResNet. So they didn't talk too much about the details of this, but they also introduced some concept called scatter connections. And the whole idea there is in the ResNet, you have the sort of positional visual features, and you take the output from the transformer, which is just ends up being a 32-dimensional vector, and you embed that into the position that it corresponds to into the ResNet. And at the very top, you can see all of the different outputs. So the first thing that the network will output is what action type they're going to take at a given time step. And that information will flow into the next decision, which is how much of a delay, whether to queue the action, which units, et cetera. So kind of a lot for one slide here. But I guess part of the takeaway is that they did create a very sort of mega architecture. And most of these things you're seeing here, other than scatter connections, are existing tools in current machine learning, but they connected them in such a way that was really well suited for playing this game. So I think that takes us to our break. Quick recap. So StarCraft is a very complex game for humans and agents. Ultimately, they had to use supervised learning or imitation learning for initializing their agents. And then after that, they used multi-agent reinforcement learning, this concept of a league with main agents and exploiter agents. So we'll take a break, but before we do, any questions about anything we've gone over so far?
To the very left, the value network. Can you elaborate more on that?
Sure, can you speak up?
Oh yeah. Oh, can you elaborate like the value network?
The value network. So I believe this is what's being used to update the policy. This is the value network that mentioned those algorithms they were using earlier, UpGo and vtrace. That's what's being used to take games asynchronously and update the prediction of expected reward at a given time step, and then use that to update the actual weights of the overall network.
We have not gone to that detail yet, but part of, as Gordon was mentioning, the reinforcement learning algorithms involve what's called a value accumulated by the agent, and that's a function of the state. Here, the state being the feature, the baseline features that you can see it right at the bottom of the screen right there. And those are fed directly into that value to give us an estimate of it.
There was the concept of Z at some point, which was known ahead of time from the KL divergence yielding. But was that the same Z that was present in the policy function of the network? Does that mean that for every value that's a joint distribution, so for every Z there's a parallel conditional part of that function?
Parallel.
Like, I might be terribly wrong here, but that there was something comma Z, so whatever conditioned on something common.
Yeah.
The KLD, the distance between that strategy and the strategy being considered.
Yep.
Yeah. So that defines of sorts like a 2D, like the second half is a joint distribution, right? Is that correct?
The idea there, so Z is just characterizing the human replay. So the actions that they took, the decisions that the human made, that's what Z is. And then they do a few things with it, but the main thing they do is compute the KL divergence between that and the output action distribution of the policy network. So the idea is they're trying to encourage the policy of the agent to look similar to the actions that a human would take. Does that make sense? So that's where they compute the KL divergence of those two distributions.
They're trying to keep them similar, so minimize them through the learning of the policies even after the supervised initialization. So
yeah,
continuing through.
Yeah, exactly. It's primarily used here in this phase, but they continue to inject it again in a couple of different ways, all the way through the reinforcement learning phase. Yeah.
And maybe we'll talk about in the second half, but one part I didn't quite get in the paper that I'd love to learn a lot more about is how they collapse the league to create. There was this mention that they take multiple, like an expanse of the league and bring it to one. Do you know what I'm talking about? Maybe I misread this.
Collapse the league. I don't remember that. So we have some graphs in the results that show all the different agents that existed in a league. My understanding was that they never sort of deleted or combined the players in the league. Each player was a distinct player and continued to be. The only thing that's really stands out is that certain players stop updating at a certain point. So their weights just become static. They're no longer learning. They're just there to help the newer agents get better, basically. Yeah, but I don't think that they do any sort of collapsing. Thanks.
I would suggest to go to the break. So can I suggest Gordon or join the online people, and maybe.
Was there anything that came out of the discussion circles that anyone wants to share or thought was they wanted to talk about? What's that?
A lot of the conversations being held back just to wait for this section to come to light.
Right. Yeah. There certainly was a lot held back.
We had some specific questions. Some people wondering about what compute was used. Some people wondering about what is a typical time frame.
Oh, okay.
Learning happened.
Yeah, I've got some information on that. So the compute structure, we were looking at it just now. Pretty sure they were using 100. So they had 12 main agents that they were training. So it was 4 for each race. And for each one of those, they had 128 TPUs. So pretty big architecture. Yeah, pretty big infrastructure. Yeah, and in terms of the training time, oh, it's a video. They trained the longest agent for 44 days, and they also trained agents at, they extracted agents at earlier time steps and evaluated those as well. So we'll see a nice graph showing how performance improved over time with training time. And if you have any more details to share about the infrastructure, you can do that too. Here's a quick video. It's about a minute, I think. Okay, so this, it's hard to see, but this red agent, the Protoss, again, the sentient alien race, this one, this is AlphaStar. And it's playing a human in this match, a top-ranked human. So not too much in particular to look at in terms of what it's doing, except for just noticing that each time it moves the camera or tells a unit to move around, that's an action. So that's an action determined by the policy. And part of the reason it moves the camera is because it's easier to, it has knowledge of what's going on outside of this view, but they're not able to make all actions without being in this view and get all information. So when they're moving the camera, the network is basically saying it wants to get more information from a particular region. And everything it's doing in this video is pretty, I guess you could say, human-like. Sometimes it will do things that are kind of bizarre. There may be a couple things here. But, and there'll be one other video later as well. And so in terms of training, they ultimately evaluated three, or these are the, yeah, so for each of these agents, AlphaStar Supervised, Mid, and Final, they trained one agent for all three races, so Terran, Protoss, and Zerg. The first one is only using the supervised signal, no reinforcement learning. AlphaStar Mid is, again, initialized with supervised learning, and then 27 days of training, reinforcement learning training in the league. And Final is the same, but with 44 days. So these are the main agents that they evaluated against humans. And this is training data here, but this is a visualization of basically of the league. So each triangle, square, or circle here corresponds to a player in the league. And I think in the end, they trained 900 distinct players. So there should be 900 dots. ELO is the metric that they use for benchmarking, I guess, skill level in training. They use a different number at inference. But you can see that the main agents are generally performing the best. Below them, the league exploiters, and then the main exploiters. The main exploiters are not meant to perform super well. They're just, again, meant to highlight the weaknesses of the main agents. So that sort of further visualizes their characterization as a sparring partner. They never were meant to go to the big leagues. They were just there to help the main agent get better. And the supervised bot, you can see, is close to the bottom. And they normalized the built-in StarCraft AI, the strongest version, at 0. So even the supervised agent is significantly above that. So that's training results. This is the actual results against humans. So you can see the different leagues or different tiers of human players. And at the very top, there's Master League, and then Grandmaster League is the highest league in StarCraft online play. So yeah, AlphaStar Supervised, you can see, is already in between the Diamond and Master League, so quite strong. And the built-in AI is below Platinum. And then you can see here, as they add in Fictitious self-play, they get closer to Master League. When they add in the prioritized Fictitious self-play, they're actually in the Masters League. Then they add that and self-play. And then they add main exploiters. And the final version, the red dot, is all of those things as well as the league exploiters. And so the scale on the left, MMR, that's the metric that Blizzard uses for ranking players in StarCraft. And yeah, so once you're in the 6,000 range, that's extremely high. And they're basically, Grandmasters are people who would probably be professional players of StarCraft, who are very likely making money playing the game. And so that AlphaStar final was able to beat 99.8% of human players, or at least it was ranked in the 99.8th percentile. So that's pretty cool. That's a really, really impressive result. If you consider that, I'm not too sure about prior research on StarCraft, but if you consider that the current best AI that Blizzard created is around 3,000, 3,500 MMR, and theirs is close to double that. So it's a really impressive result. They even played against, they played a match against someone who's considered one of the best players in the world right now. And there's a lot of debate about it because he didn't play on his own equipment, his own laptop and mouse, which is actually very important in, or his own keyboard in StarCraft. But nonetheless, it was able to beat him in that environment. So not a fair match perhaps, but still impressive. And then they provided several ablation studies and other analysis. This one is showing their APM is actions per minute. So again, they tried to cap the action rate of their agents to be in line with what humans would do. And ultimately, they found that they actually didn't perform any better if they loosened that limit. So once you get to the 200% of the limit or no limit, they're actually performing worse. And I think they theorized that could be because under those scenarios, the agent might be overfitting to particular unnecessary movements and less focus on the overall strategy. So that was maybe an interesting thing that fell out of this. In terms of the action rates compared in the games that they played against humans, compared to humans, these are distributions for the 3 different races. Here, EPM is like actions per minute, but it's effective actions per minute. Sometimes human players will just click, sort of make useless clicks. And so consistently, their actions per minute are below the distributions of the human players, including their average 99.9 percentile and their max. So this is, again, very different from the AlphaStar V1, where they were able to have those superhuman spikes in action rates. They did a good job, it seems, of capping that. And they actually got a professional player to work with them quite closely. And there's a section in the paper where he makes a statement on the fairness of the agent and claims that it is not being given any major advantages that humans would not have access to. So they made a really strong effort to create a representative agent. This distribution, the main idea here, on the vertical scale, you have different main agent IDs. So each row would correspond to one agent. And the horizontal axis is the number of training days. And so here you can get a sense as, so if you take any one row, any main agent ID, and you look at how long or how many days they have, I guess, sort of color, this blue, how far they're still a part of the overall Nash distribution of the league, you can see that pretty much all agents fall off quite quickly. So the idea is, if you take a look at agent around here, so agent 35 or 40, it will be competitive with other agents up until you have agents that have been trained for about more than, so if it trained for about, let's say, 17 days, it'll be competitive up until you start introducing agents that have trained for about 22 days, at which point it'll just get annihilated by those future agents. And so what you can really see here is none of these lines, horizontal lines, are very long. And so the idea is, as training time progresses, the skill level of subsequent agents is consistently much improved over the past ones. And so yeah, here are some of the other ablations. So I'm not exactly sure what human init is here. Some of the figures weren't super well described, but these are various human data usage characteristics that they extracted in ablation studies, and found out that all of them were significant. So everything was adding signal. And I don't know if that's coincidence or not, but it's consistent for all of the features of their architecture. Some of these we didn't talk about, pointer network, and as well the different off-policy learning algorithms that they used. Again, UpGo was the one that they introduced in the paper, but everything they found to be quite significant. I think there's one more. This is the interface. So they tried two different setups. One where they have, remember I showed you in that video, the agent was moving the camera around. They also tried playing a version where the agent would just have full information of everything that was going on without moving the camera. And so in that scenario, which is the top bar, they perform much better. So having to move the camera around the map and take actions to do so did reduce performance. But that was something that they did to be more human-like, because a human would need to do the same. You have a question?
Was it because then other parts of the map would be invisible when they move to another part, to the agents, or?
I think the main reason that you would have an advantage playing without this camera interface is you don't need to consume actions in order to gather information, or to, like, certain actions you would need to move the camera in order to perform them. And so it's almost like a penalty. If you want to perform an action over there when your camera is currently here, you need to take one action to go there. First of all, decide to do that, and then go there and use up an action.
Does the agent typically move the camera using the main screen, or does he use the mini-map as it replaces? Do you know?
I don't know if that would, if there would be a distinction there. I think it would just, it would send a HTTP request that would tell the game what coordinates it wanted the camera to move to. So in a sense, it would be like moving the mini-map, I guess, because it can just jump to any point in the map, like a human could with the mini-map. Yeah, so I think that's probably the best way to describe it. Yeah.
The 4% of the cases where it didn't win against the leak bog, which was normalized to 0 compared to
4%.
right here.
Right.
Is that because there are some games where it just has pathological performance, like it just, the spot fails outright to do anything meaningful? Is that, or do you know?
That's a good question,
What
actually.
accounts?
I'd be curious to see those 4% of replays.
Yeah.
I don't know what happened in those cases, but certainly I've got a video that we'll look at in a moment that does show you that it does sometimes make some bad decisions, or just can't deal with certain situations. And so, yeah, it's very possible that it would just sort of glitch out in certain cases. Yeah. But I don't think that the AlphaStar mid and final would be losing many games, if any, to the built-in bot. This is supervised win rate.
Oh, sorry.
So yeah, it could also be early in training. It could be part of it. Okay, so here's a video that DeepMind posted. I'll try and sort of narrate it, although there's description at the bottom, hopefully. Okay, so in this case, the main agent is in blue, and the exploiter agent is, the main exploiter is in red. This is a strategy called cannon rush, where you put these cannons outside the opponent's base and just sort of siege them in. And you can see that the main agent just doesn't know how to deal with this, and it just ends up losing. So its buildings are just getting destroyed. It can't do anything about it at this point. But then, after further training, a new main agent, which is green now, is able to successfully defend this same strategy. So red is employing cannon rush again, and green has figured out how to deal with that. The main agent knows how to counter that. And cannon rush is a pretty common strategy you would expect to see in human replays. And it's also able to beat an older main agent. So green is a newer main agent, blue is an older one, and it's just able to outperform it. This one's a bit harder to see. That same main agent is still susceptible to exploiter agents. So in this case, the exploiter has found that it can use these invisible units and just sort of wreak havoc on the main agent because it hasn't created any detection units. So that video is sort of meant to visualize the cycles of exploitation and then having main agents catch up and then sort of repeating that. And they also had a section in the paper where they, again, their mission is to solve intelligence and use it to make the world a better place. So they wanted to talk a bit how this architecture would be transferable to other domains. So they say you could do it for domains with observations that are composed of combinations of images and lists and sets. So remember, they have this idea, again, not super explained in the paper, of scattered connections, where they take the entity embeddings and combine that with the data from the map, the image data. And so they say that's one area that would be quite transferable to other domains. And as well, this idea of doing imitation learning with different specific statistic for whatever use case or game that you have. You could apply the same methodology, but changing what statistic you use in calculating your KL divergence, for example. And then they say that this league concept can be applied to any multiplayer domain. I'd like to talk about that in the discussion at the end. But I think there's just a brief recap. So ultimately, they were able to rank in the 99.8th percentile of all players, human players. And this is really the highest level of human competition. And there are plenty of replays. If you want to see more, you can go online, just search AlphaStar on YouTube, and you can see full described replays. They did a very good job of not displaying any superhuman mechanics. And ultimately, they found that supervised learning and RL were both critical to creating this agent. So that's the presentation. We have some discussion points, but maybe before that, we can see if there are any other questions from the audience. Okay.
This is a question I have. Since like 2 weeks ago, the value network doesn't have full observability of the situation.
Full observability of the environment?
Yeah.
I believe it would.
So
Was it specifically mentioned?
yeah, so the value network takes in the state, and if you go back in one of the slides, I think we had
The
a discussion
architecture.
with the state.
The architecture?
No,
Even before that, I would
Okay.
say. This quite early on. But essentially, the state in this case is composed of what is observed and also past actions that have been taken by that agent.
Oh,
So if your question is, does the state comprise of observations? Then yes, it does.
no, I mean, the full observability means no fog or wall. I mean, there's no black area in that. That is included.
The observations that compose the state are the observations that the agent is made aware of. So that would include the fog of war, as Blizzard calls it, the inability to see certain parts of the map. That is included inherently in the observations.
But is that supposed to be what actor would be able to see? The critique would just be like a real life critique. Well, you know, when it is observing, for example, the other side is doing a Gano rush, and the main agent didn't detect it. It will make a comment like it sucks. It doesn't even comment that. It doesn't even see that. So does it make sense to have different observability for actor and critique?
I don't think it's. Also, what do you mean by different observability?
I mean, the actor should see fog of war and not see what other players are doing. And the critique, the value network, should be able to see both.
Should the value network be able to see both?
Yeah.
That is a good point to bring up.
it could.
Normally in the setup of reinforcement learning, the value network is trained by the same state as is made available to the policy network.
Yeah. That's a symmetric actor critique.
That's a symmetric
I
effort.
think that they did say that they experimented with, in certain cases during training, providing full information. So that might well have been through the critic. I can't quite remember, but yeah, that was something that they didn't do for, I think, the full training, and certainly not at inference.
Well, nobody would.
Yeah.
It's impossible to do it.
They're not updating at that point, yeah.
But it's not like the paper doesn't mention that much.
Yeah, again, outside of maybe turning it off during training, I don't think they mentioned it.
I'm not sure if this is relevant, but during fictitious cell play, you have while training you can have the value network, the policy of your opponent. Is that relevant here?
Is that relevant? So it's not so much whether or not the policy of the other network is available. It's so much as should that value network have access to extra information which the policy doesn't have access to. And that if the policy doesn't have access to it, doesn't matter in that sense.
Yeah, and in that architecture picture, it's clear that they have two different bodies. One is LSTM, the other is something like I can't remember. It's just called value network. Or wait, wow. Yeah, they share the same LSTM.
The output of the LSTM is fed in.
Yeah, it's like one body, two head.
Yeah, they don't really visualize here where the output of the value network is, how that's being used to update the policy.
That's used in the loss of the policy, which is why you don't really see it on this.
Okay, I think we have an answer. The answer is no.
That it's not different.
Yeah. The critic also see fog.
But yeah, that's a good point to bring up. I've never encountered a situation where normally you would have both being available to both networks, but maybe in this case it might be possible to try a different language.
So a couple questions that I wanted to pose to everybody. First one that I mentioned earlier. So does the reliance on supervised learning here speak to a bottleneck on compute or something else? So obviously they used a really, really large architecture and large infrastructure. And even so, as you saw that quote earlier, they very much depended upon supervised learning in order to become successful. So is that because we just don't have enough compute infrastructure to be able to model things as extensively as we'd like to simulate as many simulations as we'd like to? Or is there some other bottleneck here? Is there some other reason that supervised signal is necessary? So if we had infinite, if our compute infrastructure was a million times the size of what theirs was, would that get us close to being able to remove the supervised learning, or is that just nowhere near?
I think it's still, given the size of the action space, in principle, you would eventually get there, but it's just so incredibly large. And given how structured the game is and the history of it and how much knowledge would be embedded in the human priors already, because I think they didn't just choose arbitrary human priors, they had a select group of human priors at the beginning. Do you remember which, off the top of your head, what the first, the first set of human priors were not completely arbitrary, they were something. But
I think they just randomly sampled human games, like human replays.
And later on, they had criteria for the.
I think the only criteria that I saw was just the skill level of the players.
22%, top 22% of the.
I think you said like 16,000 on the top.
Yeah, so they took initially only replays of the players who were in the top 22 percentile, and then after that they took only replays from players in the probably, I don't know, 5th or 10th percentile, something like that.
So already there, that contains a lot of structured information that would take. It gets you a lot of the way there to having meaningful and sensible actions and a constrained history. But yeah.
Yeah, they certainly showed that information was impactful and significant. There's no doubt with their ablations and just looking at the performance of their agents. But I wonder, is there, again, coming back to what I said at the beginning, you sort of felt like going into this, their goal was to be able to use pure reinforcement learning, ideally pure image-based features, and so this was in some ways perhaps, although a huge achievement, a compromise on those goals. And so I wonder what's the fundamental reason that they need to compromise? Masood?
So I think, get back to the OpenAI game that it was hide and seek, I guess, a couple of months ago. So that one was without any supervision, they were just playing against each other, right? And they caught up about the game, like what's going on and what is the dynamic of the game. There was no supervision basically, I guess. They just had rewards function of that. So it might be doable, but for like a lot of, because there are a lot of things going on in this game and there are a lot of details, it might be harder. Of course, like the dimension of the complexity of this game, I don't know how many times bigger than hide-and-seek game that OpenAI tackled. But I guess computationally speaking, if it's infinite, it might be doable. You just start doing random stuff and I don't know, like two agents play against each other and try to make themselves better. Maybe that's.
Have to be very parallelized, obviously.
Yeah.
There is a comment from online about this. So Xiyang is saying that it's such a big action space. Without supervised input, the initial agent would have played the game forever without determining a winner. Unlike in Go, you can keep making random moves, and unlike in Go, you can keep making random moves, and the game is guaranteed to end.
Mm. Right. I mean, you would, sorry, guaranteed to end?
Yeah.
So you would still guarantee that the game would end in StarCraft because your opponent would probably defeat you.
There's a concept
Right.
of tie.
The time scale.
They limited the time.
Yeah. True, that's a good point.
What if that game is stopped without anyone winning in 900 time? That is like
There's
waste
points.
of
There is a draw. You can have a draw, but I can't remember what the conditions for a draw are. Usually it's human accepting.
You get assigned points in StarCraft for every building you build, for every unit you kill, for every building you destroy, you get points. And if it ever comes down to a situation where, for whatever reason, you get disconnected or something, the points decide typically, and it would be really hard to get the same number of points. You'd have to try to get the same number of points without anything right at the beginning, because even the minerals you collect, like the resources, get you points. So
Interesting. I think you had a point earlier that you wanted to make.
yeah, I did. Oh, yes. So in the history of StarCraft, one of the weird things that happens is sort of like, for years there were like sets of strategies, but then out of nowhere someone would figure something out, like, oh, you could rush with like, I don't know, 6 drones or something. But it happened months, years after the game came out. They kept having patches come along, but it took people to figure these things out. So it's a really mature game now at this point. Do you think that maybe this question would be different for a new set of rules, and for something that maybe, like, if we didn't already have like 20 years of StarCraft kicking around, that it might pose a different learning landscape where reinforcement learning could come up with novel, unexpected things and quickly displace the top players?
Oh, interesting. Like if they had released this in the past, would it have been even more successful?
Yeah, or like if there weren't already the case that like all the strategies and the themes that went on to inform the strategies. If this game came out yesterday, maybe reinforcement learning would be much better compared to humans because it could come up with things. But the human prior the human prior in this particular case would limit that, but without that it would enhance it, I think.
Yeah, it's an interesting point. I would not be surprised if we find that AlphaStar actually will unravel or uncover new strategies to play in the game. In fact, I mentioned that it played one of the best players in the world. I saw a tweet of his where he said he was playing some other human versus human game, and he experimented with something that he had seen AlphaStar do. And so that's not necessarily like a full-blown new strategy that's being introduced, but already you're seeing people being influenced by it and it contributing new ideas. So I wouldn't be surprised if there's new paradigms that are unlocked, because that action space being so large, it's possible that there are things that humans just happen to avoid over time.
Can I ask something? Okay. One of the, like in the paper there were screenshots of like some of the stuff that like the tech tree was encoded, and numerous other aspects of the game are already encoded. Could you foresee, like, do you think anyone has ever had the goal to try and be able to figure these things out just from the video stream? Like if you sit a 6-year-old in front of the computer and say, learn how to play StarCraft against the AI and self-play or whatever, do you think that was ever a goal or will be a goal?
For an agent to do that?
Yeah.
Again, I think that Xiyang and I were talking about, I think that was sort of the flavor of their initial motivation when I first heard this a couple of years ago. I think ideally to them, that was probably when there was vision networks had become very well established, and I think they had aspirations of combining that technology with reinforcement learning to create something like a 6-year-old, an agent like a 6-year-old that would just observe and understand based on visual characteristics of the map what was going on.
There was a recent paper also from DeepMind that just takes in raw input data, and they claim that the agent figures out the rule on its own. It's fairly recent. It's within the recent like 2 weeks, and I think they mastered a bunch of board games and as well as Atari.
Yeah, Super Mario, probably the same.
Super Mario,
Like,
I don't remember.
I can't imagine they're getting any sort of tabular information in that game. I think it's all visual.
The only game they failed at is one Atari game where there's a very long delay of reward, where you have to go through many complex steps to get the reward. That one they failed. Everything else is figured out. So,
Long dependency.
yeah.
Right.
You follow it since version 1, and version 1 they had a very, they have some kind of a screw up against mana, which was heavily publicized. In which case the policy network can't remember where mana draw the two immortals
using drop harass,
behind
right?
their behind their collection zone. That's
right.
And well, constantly varying between the front line and the rear. So they publish an explanation to this.
That's a good question. I don't think they publish any explanations for strange behavior. I've seen some new things just from watching more replays of the current version. Certainly that example, which was, again, the AlphaStar from last year, that one was quite obviously, I think that one was pretty clearly a mistake. But it's been interesting, I mean, a mistake, it was faulty play. It should not have been forgetting about that unit. But in some of the replays I've been watching, AlphaStar has taken some actions like, for example, it forgot or neglected to block off enemy units from running into its base in a couple of scenarios. And that's like a very basic thing. Most players would know how to do that. And so the people were sort of saying, well, it's ridiculous. It doesn't even know how to do that. But I watched that full replay, and in the end, it wins the game. And the commentator and people commenting make the argument that it actually understood that the trade-off of letting those units go into its base and do whatever they had to do was actually potentially advantageous and arguably not a problem. So some of these things I think we might find are actually not mistakes. But that one I think was that you're referring to.
Yeah, that one it loses.
Yeah, right.
When I was watching the replays of I'm not sure how those YouTubers got those replays. Some of them we were not even able to obtain, like in other races. They only have replays for Protoss, but they got replays for Zerg and Terran, like the other two races. We have no idea how they got, but the consistent thing they comment on is how stupid AlphaStar seemingly look.
Oh.
Like they do like they said, rookie mistakes all the time, but somehow a lot of times still emerge to win.
Yes.
And so it's my guess is probably, if you look at the replay of AlphaStar, number one is it never makes a single mistake. Even if it's battling on the front, it never forgets to manage its economy. Maybe it wins through a combination of sheer persistence and just not being forgetful about the overall picture, and just it probably win by average in the end. So, or maybe it has some grander scheme that we are not aware of. So it's still a mystery. Yeah.
So basically, the most interesting part is to ask it to explain the matches that it loses.
Yeah, that'd be very interesting to look into and to find out if I'm very curious to see, this is all pretty new, the paper came out in October. I'm hoping that they'll expose their agents to more of the broad public, and so we can get more games played. I'm curious to know, are there certain strategies that people will pick up on that AlphaStar is consistently weak to? Like, did the exploiter agents do their job, or are there still weaknesses to the policy of AlphaStar? TBD, I guess. Okay, so thanks so much for all your questions and interaction, and thank you to DeepMind for this work. And to the facilitators.